Welcome back to The Explainer. We've got some absolutely massive AI news to break down today. Liquid AI is completely revolutionizing long context document processing. And the kicker, they're doing it entirely on standard CPUs. Look, if you're building AI pipelines, you already know the pain. Running massive documents through standard models without a GPU is, well, expensive and incredibly slow. But going by Liquid AI's latest release notes, that entire paradigm might have just shifted. Here's our roadmap for today. First, we'll hit the CPU inference problem. Then we'll introduce the LFM 2.5 encoders. After that, we'll peek under the hood, check out the benchmarks and speedups, look at some real-world applications, and wrap up with how you can get started. Before we jump into the weeds, I want you to ask yourself a question. Honestly, how much compute and time does your team burn through right now just doing basic routing, classification, or PII detection on long documents? Imagine being able to securely scan a 15-page legal contract. We're talking roughly 8,192 tokens here, on a standard laptop CPU in under 30 seconds. Sounds crazy, right? Well, that's exactly the reality we're unpacking today.
All right, let's start with Section 1, the CPU inference problem, and exactly what's causing the bottleneck.
Traditionally, developers have been stuck between a rock and a hard place. Option A, you fork over exorbitant fees for cloud GPUs and constantly battle provisioning dependencies. Option B, you try running standard models on a CPU, but you know as well as I do, as soon as you do that, your throughput drops off a cliff. The latency degradation just becomes completely unmanageable once you hit longer sequence lengths. Let's put a real number on that. Standard industry baselines like ModernBERT-base can take over a minute and a half. That's right, over 90 seconds just for a single forward pass of an 8,192 token sequence on a CPU. I mean, if your app needs to scan tens of thousands of documents, waiting 90 seconds a pop is literally going to destroy your SLAs. Moving on to Section 2. Enter the LFM 2.5 encoders, which were built specifically to run fast on CPU. So, Liquid AI just dropped two brand new bidirectional encoder models on Hugging Face, the LFM 2.5 encoder 230M and the 350M. And these aren't just any models. They are engineered from the ground up for lightning-fast, document-scale workloads on the exact hardware you already have sitting in your racks. They're designed to be drop-in replacements for whatever transformer-based encoders you're running in production right now. But here is where my mind was blown. The performance leap is staggering. At that massive 8,192 token context, these new encoders deliver a 3.7x speedup over ModernBERT-base on CPUs. 3.7 times. And unlike traditional baselines that just degrade the longer the text gets, the throughput curve for these LFM 2.5 encoders actually tends to flatten out as length increases. Okay, so how on earth did they pull this off? Let's get into Section 3 under the hood and look at the architecture changes. You probably remember when Liquid AI released their LFM 2.5 retrievers recently. But, retrieval is just one piece of the puzzle. To build a truly general-purpose model, they used a masked language modeling objective. Basically, this forces the model to understand bidirectional context by hiding tokens. And what's super interesting is they masked 30% of the tokens during training. That's twice as dense as BERT's classic 15% rate. This makes the model incredibly robust for things like routing, classification, and complex token-level tasks. And this perfectly highlights their brilliant architectural pivot. They literally took their existing causal LFM2 decoder backbones and Frankensteined them, in the best way possible, into bidirectional encoders, using three really specific structural tweaks. First, they swapped their causal attention mask for a bidirectional one. Second, they used symmetric padding to make the short convolutions non-causal, meaning every token gets to mingle with its neighbors on both the left and right. And third, they applied that dense 30% masking rate we just talked about. Once those structural changes were locked in, they put these models through a grueling two-phase training bootcamp. Phase 1 was all about general language competence, training on a massive web corpus at a standard 1,024 token context. Then came Phase 2, where they stretched the model's legs out to an 8,192 token context. This second phase was laser-focused on boosting the model's factual, legal, and multilingual chops. All right, let's see how this all pans out in the real world in Section 4, benchmarks and speedups. When you look at the raw data, the speedup is just phenomenal. The LFM 2.5 encoder 230M crushes that 8,192 token forward pass in roughly 28 seconds. Let that sink in. Compare 28 seconds to the 90-plus seconds you'd wait with ModernBERT-base. The LFM2.5 is completely flattening that nasty throughput curve that normally brings CPUs to their knees. Of course, speed means nothing if the accuracy is garbage, right? But the benchmark results are actually wild. Across 17 different GLU, Super GLU, and multilingual tasks, the 350M variant punches way, way above its weight class. It actually ranks 4th out of 14 models, and the only ones beating it are up to 10 times its size. And the smaller 230M version, it's beating out nearly every Eurobert model on the list, despite being a fraction of their size. Let's transition to Section 5, Real-World Applications, and explore some actual use cases. Digging through their documentation, it's fascinating how perfectly these models map to highly constrained environments. Since you don't need CUDA or GPUs, you can run serious AI workloads securely on the edge. I'm talking about a car's onboard computer or an industrial controller handling intent routing. Or think about regulated on-prem environments, like healthcare or legal networks, where data absolutely cannot leave the premises. You can run PII detection across 16 different languages, handle zero-shot prompt routing, or do policy linting, all on your own private CPUs. You can even use it as a super cheap first-pass filter before sending requests up to your massive, expensive LLMs. Finally, if you're an engineer itching to get your hands dirty, here is Section 6, Getting Started and Deploying LFM 2.5. Okay, listen up, because this is the absolute most important takeaway if you're actually implementing this. You have to fine-tune it. Fine-tuning is strictly required. Out of the box, the base encoders just produce general-purpose representations. If you try to use the pre-trained weights as is, you're going to get near-random garbage outputs. You absolutely must attach a task head, whether that's for classification or retrieval, and fine-tune it for your specific use case. Fortunately, integrating this into your stack is an absolute breeze. Just install your standard Hugging Face Transformers library, load up the auto model and auto tokenizer for whichever variant you're using, the 230M or 350M, then pop on your specific task head. Liquid AI actually provides a fantastic open source tutorial specifically for fine-tuning on long legal documents with that full 8K context, so definitely check that out as a starting point. Oh, and a quick pro tip, absolutely use flash attention too if your hardware supports it. If you're looking to serve these models at scale, I've got even more good news. The brand new VLMM version 0.26.0 now includes basic inferencing and serving support for x86 and ARM CPU platforms. This release fully supports FP32, FP16, and BF16 data types, which gives you a ton of flexibility to dial in the perfect balance between precision and throughput, depending on your specific hardware. Liquid AI wrapped up their announcement with a pretty bold statement. They said, "The edge AI future is here. We can't wait to see what you build." And honestly, I think it perfectly captures the vibe of this release. It is all about bringing highly efficient, decentralized, long-context compute right back to the hardware we already owned. So I'll leave you to chew on this. Now that you absolutely do not need an expensive cloud GPU to process a 15-page contract in mere seconds, how are you going to rethink your own data pipelines? What massive documents are you going to start crunching on the edge today? Thanks for hanging out with me for this explainer, and happy building.